Hey everyone, welcome to BCP Med. In this video, we are going to be breaking down the electronic structure of the atom in great detail. We are going to look at the hierarchy of electron orbits, starting from energy levels and working our way down to the spin quantum number, which will help us put together an orbital diagram at the end. Let's go ahead and get started. The first step in our journey is going to be the broadest characterization of electron structure, known as the energy level. We know from Bohr's model of the hydrogen atom that each electron, owing to their nature as quantum particles, can only have a discrete energy value, which is a 1 over n squared multiple of Planck's constant, where n is the quantizing index, or the quantum number. Specifically, the Bohr model predicts that the energy an electron is allowed to have is going to be 13.6 electron volts times the nuclear charge z squared over the quantum number n squared. The quantum number n, which describes the multiples of energies the electrons can have, is actually going to describe what are known as energy levels. So n is our electron energy level, and that corresponds to a very specific orbital distance in the atom. We can imagine that the energy levels of an atom are actually nested together, sort of like Russian nesting dolls, around the nucleus, such that as the n, the quantum number, increases, the energy of the electron increases, approaching a zero value of potential energy, which means there is no interaction between the nucleus and the electron. Simultaneously, and because energy and radius are correlated, an increasing n value leads to an increasing radius, such that as n increases, R1 goes to R2 goes to R3, which is larger in size. Also, while a hydrogen atom only has one electron, in other elements, each energy level can actually contain multiple electrons, not just one. And the fact of the matter is that as the energy level, or the n value, increases, the larger the sphere, the larger the radius of that energy level, the more electrons can be held there. And the reason for that is that the more space is available, the further the electrons can spread apart, minimizing the repulsion of those negative particles, which lowers the energy state. Now, a Bohr model of an energy level diagram might look something like this, where you can see the interior energy level, or the n equals 1, is going to hold 2 electrons, as indicated by the red dots around the nucleus. However, the second energy level, the second ring around the nucleus at a further distance, can actually hold 8 electrons. If you go even further, the n equals 3 can hold 18 electrons, and the n equals 4 can hold 32 electrons. So clearly, as n increases, the number of electrons can be held quickly increases as well. Another caveat is that the distance between energy levels actually gets closer, or somewhat closer, as the energy levels increase. So the distance between, say, 3 and 2 is going to be smaller than the distance between 2 and 1. The reason is that there's a finite amount of energy needed to get to n equals infinity, or the infinite energy level, where the energy of the atom, the potential energy, I should say, is equal to 0. Right? That will mean that when an electron reaches n equals infinity, it will have been removed from the atom for all intents and purposes. An energy level diagram, which represents the energy graphically, might look something like this, where the n equals 1 level is at some negative potential energy, E is less than 0, at the bottom, and as n, the quantum number, increases, each step on this graph represents a new energy level. Eventually, it will reach an n equals infinity bar, that dotted line where E is equal to 0, and that corresponds to a complete dissociation of the electron from the atom. Now, it's important to note that because electrons are quanta, their positions are probabilistic, meaning they do not actually have discrete radii or energy values, only averages and ranges. Another way to look at this is that the positional restrictions are soft. They are not hard boundaries. Rather, position is probability based, not discrete values. For example, consider an electron orbiting an atom at some radius r, which corresponds to, say, the n equals 1 energy level. In reality, the electron is not just stuck orbiting like a planet at this radius. If we were to observe the electron many times in successive fashion, the tracks it would leave would appear something like this. You can imagine this as the footprint of the electron over time. As you can see, the electron tends to be localized around this orbital distance. However, it randomly appears at different positions at each observation, including sometimes rather far from where it is quote-unquote supposed to be. A better way to visualize this, I think, is with a probability graph of the electron density. This graph here shows the probability of finding this n equals 1 electron in a sphere of a radius r away from the nucleus. The probability of being either at the nucleus or very far from the nucleus is quite low. As you can see, the probability goes to 0 when the radius is equal to 0 and as the radius approaches infinity. The probability, however, of being at the orbital radius, the average orbital radius, is maximized, and that corresponds to the peak in this graph. However, the electron can and does exist with some probability across all of these radii values, however small the chance may be, and the height of the graph corresponds directly to the probability of finding it there. So these energy levels, while they do represent the allowed positions of the electrons, are really more a general shape of the probability distribution, which is a result of the quantum mechanical wave function. The next gradation down in terms of electronic structure is going to be the sublevel, which is going to be defined by the angular momentum quantum number L. The way in which the spherical wave function interferes with itself means that the shapes of constructive interference are not all going to be spherical shapes. Indeed, every energy level is actually subdivided into distinct shapes known as sublevels. Right, so each energy level is going to have different shapes nested within it, which are called sublevels. Now, sublevels are identified, as I noted earlier, by their angular momentum quantum number, L, which can have any positive integer value, starting from 0 and going upwards. And the L is often represented as a script L, and the sublevels are often also referred to by letter designations rather than just their quantum number. And that's summarized here in this chart below. So for example, an L equals 0 sublevel would be named an S sublevel. An L equals 1 sublevel is a P sublevel. L equals 2 is D, L equals 3 is F. And those are the most common ones that you will see in an atom. In theory, there can be more, but these are the only ones that matter in terms of chemistry. Now, you will notice all of these are distinct shapes, right? And these can be represented by the pictures below. Now, these are two-dimensional pictures. In reality, the orbitals are all 3D, but this gives a good idea of what the shapes look like. The one on the left is S, which looks sort of like a sphere. The dumbbell-looking shape in the second position is the p orbital, or the p sublevel rather. Then we have a d sublevel, and finally an f sublevel. And you notice the shapes get more complicated as the L value continues to increase. Now, there are actually some energetic restrictions on the sublevels based on what energy levels, n, in which they can appear, right? The larger sublevels are actually going to require more energy, right? The bigger energy levels will then be needed for those higher L sublevels, right? F is going to be higher in energy than D, which is higher than P, which is higher than S, and so we need larger energy levels to hold those higher energy orbitals. And so the allowed sublevels are given by L must be less than or equal to n minus 1. Now, what does this mean practically? Well, those results are summarized here in the chart below. The n equals 1 energy level can only hold an S sublevel, whereas n equals 2 can hold both S and P. N equals 3, SP and D, and n equals 4, SPDF. Anything above n equals 4 can hold all of them, no problem, right? As a result of this, you will never see small atoms, right? Atoms with low energy levels, like hydrogen or helium, having an F sublevel at the n equals 1 position. It just won't happen. The energy level is not large enough to hold those complex flower-looking shapes. It can only hold the simple spherical S orbital. Another important fact to consider about sublevels is that even within the same energy level, they are going to be at different energies, right? So I already mentioned that the sublevels are at different energy values, but I really want to clarify that is within the same energy level also. That is not just on the whole in abstract space, right? The higher L sublevels like F and D are going to be higher in energy than the lower sublevels like S and P. The position of the electron within these orbitals, though, is a little bit complicated, and why that leads to different energies is not trivial. So let's go ahead and explore that a bit. If we consider the shapes of the 2s and 2p orbitals below, we'll see something interesting. Right? So the 2s orbital is this spherical-looking orbital, and the 2p orbital is this dumbbell-shaped orbital. And their electron probability graphs are shown here below, with 2p corresponding to the red orbital and 2s corresponding to the blue orbital here as shown by the graph. If you notice, the most likely position for the p orbital, the peak of the distribution if you will, is closer to the nucleus than the most likely position of the s orbital. However, the s orbital also has this small bump closer to the nucleus. You could say that the s distribution is bimodal. It has two common values. And that is actually very significant. The reason is that while the p's most likely position is closer, the peak is closer, on average, if you were to sum the average of the probabilities, the s orbital tends to be on average closer to the nucleus. And proximity to the nucleus is directly related to energy. The closer you are, the lower energy state you're in due to that Coulomb electrostatic interaction. And so the s orbital, because its average position is closer, is actually lower in energy, right? And as a result, the energy of the sublevels can be ranked as SPDF in increasing order. There's also an interesting phenomenon that occurs, and that is known as energy splitting between the sublevels. What that means is that the D sublevel and the F sublevel actually intervene between the energy rankings as the energy levels change. Now, let's break that down a little bit. So the D sublevel can actually be slightly higher in energy than the S sublevel of the n+1 energy level. So a 3D orbital can be higher in energy than the 4s orbital, right? And that leads to some rather tricky effects when it comes to how electrons fill into the atom. Now, the result in an energy level diagram looks sort of like this, right? If you have the n=4 energy level and the n=3 energy level, on average, 4 will be above 3. We know this. It's going to follow the Bohr distribution of 1 over n squared. n=4 is going to be higher. However, as you can see, they cross over. The n=4, the S sublevel, is lower in energy than the n=3 D sublevel. A simple way of thinking about this is that as the higher sublevels increase in energy, right, as the D and F increase in energy, they start to overlap with the bottom sublevels of the energies above them. Almost like, if you can imagine this hierarchy increasing upwards, as they start to split apart into these individual sublevels, the tops and bottoms overlap. And that's exactly what's happening. And a similar fact happens with the F orbitals and the n+2 S sublevel. And this leads to the D and F blocks in the periodic table being their own separate thing rather than mixing and matching with the S sublevels and how the electrons fill into the atom's structure. Now, the next step down from sublevels are going to be orbitals, which are the actual orbits the electrons follow in their path around the atom, or more accurately, to use a quantum picture, the shape of the wave function for one particular electron within that sublevel. Each sublevel is going to be divided into these distinct orbitals, which are really geometric spatial subdivisions of how the sublevel breaks down in three-dimensional space. For example, let's consider the three p orbitals here. Each p orbital points in one Cartesian coordinate direction, either x, y, or z, which represents the path of this particular electron within the p sublevel within a given energy level. So it's this sort of further spatial subdivision. One electron does not occupy the entire p sublevel, only one of these particular orbits within it, which have these characteristic dumbbell shapes. And these three p orbitals are said to be degenerate, which means they're all exactly energetically equivalent, outside factors notwithstanding. So an electron has no preference for which one it goes into or which orbit it takes, only that it will be constricted to one of these three. It cannot occupy all of them simultaneously. It is also the case that larger sublevels will contain more orbitals and therefore can hold more electrons, right? So we said earlier that the f orbitals and the d orbitals can hold more electrons than the s and p, and the reason is because their more complicated shapes and higher energies can accommodate more spatial directions. There's more possible spatial arrangements for the electrons to orbit within those sublevel shapes. So the sublevel can be denoted by the quantum number m sub l, which designates a particular orbital within the sublevel. And it can take any value from -L to L. right? So as the L value gets larger, there's more possibilities. So let's consider the following chart here, which shows us our L values, our sublevels, and their letter designations as PDF. The next chart, which is added on to the right, is going to give us the possible M sub L associated with these sublevels, and therefore the number of orbitals. So as you can see, the L equals 0 sublevel, the S sublevel, can only have 0 as its M sub L, right? It's restricted from 0 to 0, and so there's only one orbital. The S sublevel can only hold one orbital. Conversely, if you go down to the P, we see that L equals 1 can have values of -1, 0, and 1, each of which designate a distinct orbital, and therefore the P sublevel can hold 3 distinct P orbitals, which are shown above, the Px, Py, and Pz. And that goes onwards, with the D and the F holding 5 and 7 orbitals respectively, based on their quantum number L. Now, because each orbital can hold 2 electrons, a fact we'll come to why that is true in a second, but each orbital can hold 2 electrons, and so the total number of electrons each sublevel can hold is going to be given by 2 times the number of orbitals, 2, 6, 10, and 14. And this is where the number of columns inside each block of the periodic table comes from. The S block, the alkali and alkali earth metals, are only 2 columns wide because the S orbital can only hold 2 electrons. The S sublevel, I should say, can only hold 2 electrons. The P sublevel can hold 6 electrons because it has 3 p orbitals, 2 electrons each, and so on. Our final identifier is going to be the electron spin. Spin is an intrinsic property of all quantum particles. However, and I really cannot stress this enough, it is not actually that the particle is spinning. Electrons aren't even really particles, they are matter waves. So there isn't anything to spin, there's no sphere or basketball spinning in space. However, like real spinning spheres, the matter wave has an angular momentum associated with it, which is determined by the sign of the wave function. So it is useful, if not entirely correct, to look at spin as a proxy for a real particle spinning and the angular momentum that comes with it. Now, electrons can only have 2 spin states, which we can extrapolate from the classical analog, from the real spins. The first is going to be spin up, which is going to correspond to a spin quantum number m sub s of +1/2. Don't worry about why it's 1/2, it comes from the solution to the wave function. Just be aware that electrons will have half integer spins. So if we were to look at this classically, a spin up electron would correspond to a sphere that is rotating counterclockwise, and this comes from the right-hand rule of angular momentum. A spin-up electron has an upwards pointing angular momentum, which corresponds to a counterclockwise rotation of a sphere. Electrons can also be spin down, which is m sub s equals -1/2, and that would correspond to a classical sphere rotating clockwise, which means the angular momentum of the sphere would point downwards. And if you haven't taken physics, don't worry about why the angular momentums are in that direction. Just know that that is the convention, and that electrons can have either +1/2 or -1/2 spin. There's a phenomenon associated with this spin known as Pauli exclusion, which requires every electron to have a distinct set of quantum numbers in the same quantum state. So within a given atom, each electron must have distinct quantum numbers. An orbital within an electron, right, which is the spatial subdivision of the sublevel, has the given quantum coordinate n, l, m sub l, the energy level, the sublevel, and the distinct orbital. So for example, the px orbital will have an n equals 2 energy level, let's say, an L equals 1 angular momentum quantum number, and an m sub L magnetic quantum number of somewhere between -1, 0, or 1. Now, an electron in a given orbital will have a quantum number of n, L, m sub L, m sub s, where the m sub s distinguishes whether or not the electron is spin up or spin down. Because spin is our last quantum number, and it's restricted to only 2 values, only 2 electrons could possibly exist in each orbital, since for a given orbital, all the other quantum numbers are going to be the same. So because m sub s has only 2 values, each orbital can only ever hold 2 electrons, right? There's no possibility for the spin to take any other value. So if you have 2 electrons in the p sub x orbital, they're going to have the same n, l, and m sub l values, but the m sub s will be plus 1/2 and minus 1/2, and those two are going to be distinct electrons, and there can be no more electrons because you can't add another spin value. The result of this complex hierarchy and coupling of electrons into orbitals is an intricate structure best represented by an orbital diagram. An orbital diagram presents the electronic structure visually, assigning each electron and all 4 quantum numbers, and then ranks the electrons in terms of their energy, which in turn simultaneously ranks their distance from the nucleus, since energy and distance are correlated. An orbital diagram looks something as follows. The individual boxes represent distinct orbitals, where the row represents a given sublevel, which are all branched from a main line which indicates the energy level. So we can see, for example, let's go ahead and look at the 2p orbitals. The 2p orbitals are above the 2s orbitals in terms of energy, which means they're higher in energy, and the 3 boxes correspond to each of the p orbitals, x, y, and z. They are branched with the 2s from the n equals 2 energy level, which contains both the 2p and the 2s orbitals. If you look at n equals 3, you see it will contain both s, p, and d orbitals, each of which has a corresponding number of boxes as given by the number of orbitals a given sublevel can hold. Now, because the orbitals are degenerate, that's their equal energy, they're all in the same position on a given row, right? The sublevel, the orbitals are all side by side, indicating that they're all exact same energy, and they're all going to fill with electrons without preference. They'll become filled before filling the next sublevel. The individual electrons are denoted with arrows, which are either spin up, which is an arrow pointing up, or spin down, which is an arrow pointing down. We'll go in depth into how the orbitals are filled using the Aufbau principle and Hund's rule in the next video, but for now let's just appreciate the complexity of this electronic structure and how all of the electrons are neatly sorted into these individual subdivisions. With that, we've actually reached the end of the content for this video. Thank you guys so much for watching, and if you enjoy what you saw, please go ahead and like and subscribe to the channel. Make sure to check out our other videos on the chemistry playlist to learn more, and if you're looking to branch out, check out our other science playlists. See you next time!